start chapter 7, which the entire chapter is what we call techniques of integration, how to integrate really messy stuff. The section we're doing next time, Thursday, is, if you look at that section, 7.2, it's called trig integrals. And for some people, trig integrals are no problem, but there are always people in calculus who like to say, oh, I just don't remember my trig, or I don't know my trig. Please don't say that out loud for me to hear, because it really disturbs me. It's like if you were in an English class and they wanted you to write an essay and you say, I don't remember my alphabet. I mean, it's just not an option. So if you were going to say it or you're thinking it, if your trig is rusty, you want to brush up on it. Not just for the next section, but pretty much for a couple other sections in chapter 7, all of chapter 10, and a few other things coming up this semester. Pretty much the rest of your mathematical career, you need to know your trig. So what I did, was that last semester here? The semester before. Recently, I had a little mini drop-in session where I just kind of gave a little trig lecture to everyone and said, here's some little brush up to remind you what you should and shouldn't know about trig and some quick ways to think about it. And Nick recorded it and we put it on YouTube. And I have notes that follow along with it if you want them. Yes, sir?
Speaking of YouTube, do you know when you're going to upload the lectures?
No, we don't know yet. Do we, Nick? No, there was a little glitch in the beginning of the semester, but so we don't know yet. We're hoping soon, but once they're there, they should be coming up regularly, but they're not there yet. So we don't know yet. But the YouTube one with the trig is already up there.
Yeah.
So I have this handout for anybody who wants one. It even has the little YouTube link at the top. You can always just search my name. Most of what you'll find is statistics if you search my name on YouTube. But it has the link to the specific video. If anyone wants a copy of these handouts, you can watch. How long is the video? Anyone remember? Anybody see? I know I see people here watching.
You have one that's like an hour long, and then you have a couple that are like 30 minutes.
For trig? There's only one trig one though.
No, I don't know.
So questions about that? What that's for? That's on your free time for fun. I had like a drop-in session like one Friday for a couple hours, or it might be a 2-hour-long video. I don't remember. It was a while. But you can skip around and do whatever parts you need to. All right. So let's go on and do some more calculus. Trig was a couple semesters ago, theoretically, right? We left off last time with the. Are we good here? Still working on work problems? We'll talk about it. Maybe if you break, you can ask me and I'll break the tie. We'll see who's winning the debate. Can I have a little bit of focus? Thank you. Last time we left off with the average value of the function. And we said that the F average, to find F average, we were going to do what? How do we find it? What's the general formula for finding it?
1 over b minus a
Thank you.
times the integral from a to b of f.
Beautiful. So we integrate the function from a to b, and we essentially divide by the length of the interval that we're integrating over. That's how we found F average last time. That's where we left off. Remember that? A while ago, last week. Okay, so that was the first half of this page. I'm on page 23 of our notes here in 6.5. So we talked about that. So in the visual, remember the integral right here, just the integral portion of it, that represents the total area underneath this blue line. And then F average is the y value here that would give you a rectangle that has the same area. This height times that width should equal the same area. That's where that came from. So the mean value theorem comes next. The mean value theorem says that if you have a continuous function, there's a specific definition of continuous. A visual definition of continuous is you can draw it without picking up your pen. There's no holes or jumps or gaps in it. If you have a continuous function, you're guaranteed that somewhere in between these two endpoints, there is a x value, which they call c, like in this case it appears to be here. This c right here has the exact same y value. F of c, that's a c, sorry. Okay, I just messed that all up. I'm trying to fix it and it got worse. Let's label the whole point. This point has an x value of c and a y value of f of c, right? see f of c? There's some point where the y value here is exactly the same as f average. I mean, it has to. How can you get across there without touching it, right? So somewhere in there, you're guaranteed that the average value is the same as the y value for at least one c value. There could be lots of them. If it kept wiggling up and down, there might be plenty of them. But you're guaranteed at least one. So it says there's a value, x value c on that interval such that it makes this statement true. F of c equals f average equals, and then it restates that formula that we just talked about. Questions on what it says, what it means? Okay, so let's do an example of it. I'm just going to give you one example, pretty straightforward. So here's example 2. Example 2 says find the c for this function on this interval that satisfies the mean value theorem. That's my abbreviation for mean value theorem, MVT. Mean value theorem for definite intervals. So the question really just saying, find me which x value has a y value that's the same as the average. Let me say that again. Find an x value whose y value is the same as the average. What do you think I should do first? I want my x to have the same y value as the average value. So what do you think I need to know? Ooh, I see you whispering over there. Jamie's saying it quietly. She says, you need to know the average. I better first find what the average value is, and then I can talk about which x has that same value. So I first need to find the average, f average. So f average in this case, for this function, is going to be, what am I starting with? 1/3 I just heard? 1/3 minus 0. Okay. Integral from 0 to 3 of my function. We can find that. 1/3 integral from 0 to 3 of x squared dx. When I integrate this, I'm going to get another 1/3, right? Because that'll be x cubed over 3. 1/3 x cubed, evaluated from 0 to 3. Is with me? That's 1/9. 3 cubed minus 0 cubed. The answer is 3. 27/9. That's not the answer to the question. That's the answer to f average. That's the average y value. So if you think about it, from 0 to 3, my x squareds are anything from 0 to 9, because 3 squared is 9. Your y values are all between 0 and 9, but the average one is only 3. Does that seem weird to you? They go from 0 to 9. I want a picture of this. Right? Here's a point here, 0, 0. 3, 9, because it's x squared. 1 equals x squared. And what do you think, just from the endpoints, the average should be about? 4.5, right? Halfway between 0 and 9 seems like it should be 4.5 would be the average y value. What's the graph look like of x squared from here to here? It's parabola, right? So it looks something like this, roughly. Look at your y values. Here's 3 roughly and 6, pretty close. That might be a little too high. You see how about half of them are below this line? And half of them are above that line? It's not about just the y values themselves, it's about how many of them are higher or lower. And because this graph starts off so low, stays low for a while before it gets steep, you've got a lot more y values down low than you do up high, which is what brings the average down to 3, as opposed to what your brain thinks, why isn't it halfway between the endpoints? If it was a straight line, it would have been 4.5. So that's the average value. Okay, but that wasn't the question. The question said, find C for that function that satisfies the mean value theorem. The mean value theorem says that f of C has to equal the average. So in this particular case, f of C has to equal 3. Because that is the average that we just found. What's f of C? What's an expression I can write for f of C? X squared, but if I put a C in there, it's C squared? Okay. So we need to know which C value has this answer. F of C is C squared. We want C squared to equal 3. C is plus or minus square root of 3. But in our interval, the only one that matters is the positive square root of 3. So this is the x value whose y value is the same as the average. Square root of 3 is 1.7-ish, I think. 1.7-ish, maybe it's about here. I don't know. Does someone have a calculator? I think it's 1.7-ish. Someone have a calculator handy?
1.732.
Okay, so it's around 1.7. So what we're saying is, this is the x value, and when I go up here, I'm gonna fix my graph. Watch me adjust it to make it match what my statement is. There you go. Power of the eraser. Visually, you better know. This x value has a y value right here. At square root of 3, the y value is 3, which happens to be that value of the f average that we talked about. So our answer is just square root of 3. We're just guaranteed there's at least one. Sometimes there's more than one. Your graph does this, and your average is here. Look at all these values that touch it, right? Could be 3 different x values or something. You might have to solve for more than one. But essentially you're just setting your function equal to your average. And solving. Questions? Yes, no, okay? Solid 6.5, not much there. Okay, so we're gonna move on to 7.1. All of chapter 7 is techniques of integration, so I'm flipping over to page 27. Page 27. Integration by parts. So you might be in the math lab asking someone to help you with an integral, and they're like, how do I start this? And I go, oh, you need to do that by parts. They're referring to integration by parts. Integration by parts is, here's what I like to call it. You guys remember the product rule for derivatives? It's the product rule in reverse. Ah, what? That's really what it is. I'll show you why. It's the product rule in reverse. So on the top of page 27, the first one at the top before we even do integration by parts, let me label this up here so we don't forget what we're doing. The first integral is technically one that we should already be able to do at the very top of page 27. It looks like this. Nice and messy. And it says here that we've already seen the substitution method, and here's our example. So my question for you is, why is this particular one a good candidate for the substitution method? Use substitution? Yes? So there's an ln x inside the parentheses. That's half of it, right? There's some function inside there. And there's something else that makes it a perfect candidate. Yes?
Would be the something over x.
Yeah, the something over x, because what's the derivative of the ln x he's talking about? 1 over x, so we've got 1 over x in here as well. So you're always looking for 2 things when you're doing substitution. The function that's inside, and its derivative hanging around somewhere. So this actually is a perfect use of the problem. If we let u equal ln x, then du is, hopefully you remember this, 1 over x dx. And if you have to, we can break it up even so you see it better. So this would be cosine of ln x, and I could pull that other x all the way over here. I just kind of move it over there and make it a 1 over x so you can separate the two pieces if you need to see it better. Agree it's the same problem? So this is now cosine of u, because that's what we chose for u. And all of this, all of that, is du. Okay, the substitution. Now we could easily integrate that. What's the integral of cosine? Sine. So the answer is sine u plus c. But because the original problem had x's in it, we're going to go ahead and put the x's back in. U is equal to ln x, so we put that back in there. That's my answer. If I wanted to check to see if that was right, what do I need to do? Take the derivative of it using what rule? The chain rule, right? Because there's a function inside there. So if you take the derivative using the chain rule, you first take the derivative of this part, which is cosine ln x, times the derivative of the inside, which is right back to where we started. So the chain rule is actually what u substitution is doing. It's the chain rule in reverse. Yes, sir?
And so wouldn't the u substitution just take out like a step almost compared to the chain line?
I couldn't hear the other part.
Wouldn't the u substitution just take out a step and be easier than using the chain rule though? Is that how we use it?
It's actually the same thing, but in reverse. So the chain rule is when you're taking a derivative. So you have to use a chain rule to take the derivative. U sub is doing integration, so you're working backwards using the chain rule essentially. We don't call it the chain rule, but it really is. It's integrating with the chain rule. Because that's what this is doing. It's taking that derivative of the inside and starting with that part. So I don't know if you could say one or the other one's better. It just depends on which direction you're going, the derivative or the integral. So hopefully you've done some practice on those problems I gave you, and you're pretty good at U sub because they're going to keep showing up everywhere. And those are going to be the easiest ones we see are the U sub problems. So the next one is going to be the integration by parts. They don't always work that nicely. Before I show you the formula, I want to actually look at the one on the next page just to kind of talk about it. Should have two of them there. I have two of them look like this. Either one though. What if we look at example one on the next page? I'm going to bring it over here. I'm not ready to do it yet. I just want to look at it and see why it's not the same. Why it doesn't work so nicely. So example one on the next page has x squared sine x dx. So the question I have is, why wouldn't I use U sub on that one? I didn't hear you say this.
There's nothing that would like cancel out.
Yeah, there isn't a function on the inside, for sure, right? Like here we had an inside function. And if you take the derivative of either of those functions, either the x squared or the sine, the derivative isn't there in the problem anywhere. It's like you can try all kinds of things for u equals and you're not going to get anywhere. So this is an example where u sub doesn't work. And so what we need in this case is integration by parts. Integration by parts is really the product rule in reverse, which is what I'm about to show you if I don't lose my notes. Okay, so back on page 27, I actually have the product rule written there. Remember the product rule, it says, and it looks this way. If you have the derivative of two functions, you're trying to take the derivative of two functions multiplied. You'll remember that we took f of x times the derivative of the other function plus g of x f prime of x. The order that you learned it depends on where you took it, which book you used. But you always took the derivative of one function times the other one, plus the other function times the derivative of the first one. Remember that product rule from somewhere? Okay, so I wanna rewrite it using integrals. So that's my next line, we're gonna fill that in. And I'm also gonna take a little shortcut, I'm gonna drop all the x's and just call them g's and f's for the minute, it'll be a little bit easier. So if I clean this part up, just to talk about it, this is f times g, and this is f g prime plus g f prime, roughly. Just, otherwise when we rewrite it, it would carry around too many x's. The same idea. So if I wanna rewrite it using integrals, if the derivative of this equals that one, then what must be true? How can I rewrite this statement with integrals? Yes, sir. Should
The
I-
integral of the one must be d over dx.
Yeah, he's pointing over here. So the integral of this one should be what we started with, right? If this is the derivative, when we integrate this, we should get back to here. So let's write that. F times g should be the integral of this one. Agreed? Technically, there's a dx, so I'm going to put it in there, integrating with respect to x. If the derivative of this equals that one, then the integral of this equals the other one. So far, so good. I'm going to do some distributing. I'm going to say f times g equals this integral, f g prime, plus this integral. I'm writing them separately. I distributed this integral to those two terms. That's still true? Still just working with the product rule that we know and love. Just writing it backwards. So what I want to do is I want to solve for this term. What is that term equal to? F g prime dx equals,
FG minus the integral of G.
great.
F.
Chad says fg minus this integral. Right, just basically moving this one over to the other side. Minus the integral of g, I lost my place, f prime dx. Just kind of root move things around. What I'm doing here is deriving the integration by parts formula from the product rule formula that you already know. You don't actually have to ever write this part out again, and we're going to talk about a formula to use, but to me it always helps to know where it came from. In case you forget it, you can get it back again by using what you know. Okay, so when I said we rewrite the integrals and we rearrange, we should be here. So this is right about the middle of the page, right after it says and rearrange. So the integration by parts formula right underneath there looks like this. U dv, integral, excuse me, of u dv equals uv minus the integral of v du. It's right underneath there, I already printed out for you. You see it there? The u is your f function, and the v is your g function. So it's really the same product rule that you knew and loved. They just stopped calling them f and g, and they're calling them u and v. But this says you have a function and the derivative of another function. So it's like f and g prime. Right? Here's my f, here's my g prime. We're just changing variables. F and g. Right? Here's g, and the derivative of f would be du. So what this integration by parts helps us do is when you have multiplication is the best case. Whenever you have multiplication, these are multiplied together here, that's a sign that integration by parts will probably help you. There are some cases where you don't have multiplication, but you actually kind of do. It's in disguise. I'll show you one of those. That's typically when you're going to use integration by parts, when you see some multiplication and you can't do a use of. This little formula you will probably have memorized within the next couple days, like if you start doing your homework. That's how many times you're going to use it, and it's just going to keep showing up here and there. Okay, so it says, when do we use integration by parts? Most common is when you see multiplication. Most common is multiplication, like this example over here. These two functions are multiplied. It's a pretty good clue that we should probably try integration by parts. your first thought should always be u substitution. I'm going to teach you so many techniques of integration, and later on I'm going to say, you know, you could have just done that with u sub. You try all these other hard things. Don't assume that u sub won't work. Always check it first. So if you see multiplication, the second one is if u sub fails. So maybe you tried u sub and it didn't work. That's usually a sign that I better try something else. I tried u sub and it failed. Maybe I see some multiplication. And the important thing is, I don't think this is a word, but I'm going to use it anyhow. Integrable. No, that's not a word. Integratable? I don't know what the word is. If able to integrate it. You have two functions and you're able to integrate one of them. Right? We'll talk about which one is which. Integrable? That's not a word. I just made it up. It sounds good though. What do you think the word actually is? Able to be integrated. Integratable?
Integratable.
And you put another syllable in there, you think? Integratable? Integrable sounds good enough. Integratable? Let's put it on there. I like integratable too. Can you tell I don't have an English degree?
It's integratable.
Is it? Did you just Google it?
Yeah.
Thank you for Google. I was going to say, I'd ask an English teacher, but how often does an English teacher talk about things that are able to be integrated? Not very often. Integratable? I like integrable better. Kind of stumble over it. Okay. We don't quite understand this one yet because we haven't done the examples, but I'll show you what I mean as we start working through some examples. So this is why you would want to do integration by parts. So I wrote example 1 up there, but I actually want to do that one second. I'm going to actually start with example 2. It makes my point better about the integratable. There, I said it the other way. Integratable. I'm going to start with example 2 on the next page. Looks like this. Example 2. I have the integral from 1 to 2 of x squared natural log of 4x dx. Is that your number 2? What'd you say?
So we'll use u sub for.
Yeah, we could try u sub. We should always consider u sub first. Always. If I'm considering u sub, what would you consider for u?
4x.
Yeah, 4x. But the derivative of 4x is just 4. And I still have this x squared out here. If this had been 4, then I would have felt good about it. But because there's another function out here, that u sub's not going to get us anywhere. The derivative of what you choose for u has to be hanging around, or the u sub's not going to get you anywhere. So u sub already failed. You can write it out if you want to, but the x squared is going to be in the way. Because I'll have x squared times the natural log of u, and then what, right? So then what I need to do is I need to break this up and think of it as a u function times a dv function. U times dv. They are not always in the order that you want. So we could think about, I'm going to write this in green so I erase it in a minute. You might think about it this way. Like maybe I'll let u be x squared and dv be everything else. I'm about to erase this, by the way. You can write it down if you want, so write it tiny or something. So we agree that that's a multiplication. I have to have, whatever's there has to be some u times dv. But if this is dv, I need to be able to integrate it because I need to find v. If you look at this formula, if you have u times dv, I need to know what the u function is and what the v function is. So if that's dv, that's the derivative of v. I would have to integrate it to find out what v is. Does anyone know off the top of your head how to integrate a natural log function?
Something absolute value.
Yeah, there's an absolute value there. I'm actually going to show you how to integrate it later. But most of us don't know how to integrate a natural log. Right? I don't know how to integrate that. That's what I mean by dv has to be integratable. Whatever you choose for dv, you better know how to integrate it. I don't know how to integrate that. So guess what I'm going to do? Say that again?
Make up the original function.
Yeah, switch it back to the other way around. Let this one be u and that one be dv. Doesn't matter, right? As long as I know how to integrate one. So let's switch them. So that didn't work. I'll let u be natural log of 4x. And then dv will be x squared dx. Make sure you include your dx there. Well, this is my u, and the x squared dx is now my dv. We grade still u times dv. Here's why it's going to be better now. Because I need to now find v, which means if this is the derivative of v, to find v, what am I going to do with it?
You're,
Integrate it, yeah, which would be 1/3 x cubed. You don't need your plus c's in the middle of a integration by parts problem, by the way. See what I did there? If we chose this, these two multiplied out to be the original problem. If that's dv, I have to find v. Because the formula says if you start with u times dv, you need to be able to multiply those two. So I need to know what u is and what v is. We now have that. But I also need du. I also need a du. So du here is the derivative of this guy. The derivative of this guy. So be careful. We integrated this one. We have to take the derivative of that one. What's the derivative of natural log 4x? 1 over 4x times 4, chain rule. Right? Chain rule. dx. I'll bring it down here. So that's just 1 over x. We simplified it down here. You always, either off to the side or before you start, you want to make sure that you have u, dv, v, and du all clearly labeled somewhere, because we're going to plug them into that formula. Before I go any further, are there questions on what I was just doing there? How I got any part of it? No? Okay. So I'm going to rewrite this over here because I just need a little more room. So this original integral, that's the original integral here. That's my u times dv. Right? This is my integral of u times dv. I now have to take u times v minus the integral of v times du. That's the formula over there. So equals. What's u? ln 4x times v, 1/3 x cubed. That's uv. Minus the integral of v, 1/3 x cubed, times du. Du is here. 1 over x dx. There's a lot of mess going on there. So here's the original problem. We chose a u and a dv. It's equal to our u times our v minus the integral of our v times our du. Those of you who've been getting a little sloppy with your notation, I happened on your, some of you haven't gotten your labs back, I'll pass them back at the break. Some of you will write an integral when you've already integrated. Some of you will put it on there and take it off and put it back on. It really matters in integration by parts, because this is done. This still needs to be integrated. I need to find the antiderivative of this part, but not this part. You can't just willy-nilly put these integral signs on and off. They matter. So some of you are going to get caught in that if you're one of the guilty ones so far. So I'm going to simplify that a little bit. Most of the time I bring all this to the front just because otherwise it gets confused with that natural log. It doesn't really matter. I think it looks prettier in the front of the natural log. So that's my first term. That term's done. But now I have to integrate this, which is 1/3 x squared. When I simplify it, make sure you simplify here. Once you multiply, simplify before you do anything else. I have a lot of people who think of it as, oh, I have to do u and dv again. No, you don't. Just simplify it first, and maybe you can integrate it. So the original problem equals this mess minus this integral. This is still an integral, so guess what I'm gonna do with it? Integrate it. But this is something we know how to integrate. That's the whole goal with integration by parts, is you do this little ugly formula, but then you end up with something that you actually do know how to integrate. So this part I'm recopying. Oops, I lost my bounds, I better put them back on there in a second. You saw it, now threw them out the window. Let's integrate this. What's the integral here? 1/3 times another x cubed over 3?
So then you get
1/9 x cubed, yeah? So you see what I just did there? I had to integrate again. This guy. And then all of this, I dropped my bounds, it's gonna get evaluated between 1 and 2, but I'm going to simplify it first. Technically, as soon as I integrated here, I had to evaluate, these are still there. I haven't evaluated them yet. But you're not going to evaluate them until you integrate everything, do it all at the end. So I'm going to simplify one more time before I evaluate. Minus 1/9 x cubed. All of this evaluated between 1 and 2. What's going on here?
Then you just plug in here.
Yeah, now I'm going to plug in my 1 and my 2. Before I do that though, I want to make sure we understand what we just did. This right here was the original problem. It was a messy multiplication problem. We didn't use sub, we could have tried it, didn't work. So we started with this messy integral. We broke it up into this term minus a new integral. We actually took that new integral and then integrated it. Then we had this first term plus that next integral. Now we're just going to evaluate. That's always what's going to happen with integration by parts. You have this multiplication minus a new integral. Now we have to start plugging everything in. Let's see what happens. Looks like it's pretty messy to me. 1/3 times 2 cubed, natural log of 8, times 2, minus 1/9 times 2 cubed, minus 1/3 times 1 cubed, natural log of 4. Plugging in my 2's and my 1's everywhere, carefully. I'm gonna make it here before I run out of room. 8/3 natural log of 8. That's 8 over 3, right? Minus 8/9. That's this guy. Minus 1/3 natural log of 4. That's this guy here. And then this will be plus 1/9. Distributing, I got that plus. So 8/3 natural log of 8. This will be minus 7/9 because I'm combining like terms. Minus 1/3 natural log of 4. Technically, you could do some simplifying with logs and combine those two if you wanted. I'm not that worried about it. WebAssign will take it either way. Nice messy problem. A lot going on here with integration by parts. Those of you who, oh yes ma'am.
Question. Should I say it out loud or should I should?
Try to say it out loud. If not, I'll look at it. So everyone's gonna wanna know what it was.
So there you have 1/3 x to the second power. Couldn't it be third?
Yes? So right here I have this, and then what's the rest of your question?
So I'm not sure, maybe I'm not seeing it.
How I went from there to here?
No, so that should be v, wouldn't it?
Well, this part right here?
Yeah.
So this part came from right here, which was, I don't remember which one it was now. Oh, this was v times du. I was using the formula here. So I plugged v in and I plugged du in. but then I multiplied them together. So x cubed over x simplified to x squared.
Oh, yeah.
So we're just simplifying this down to here.
Okay.
You see it now?
Yep.
Okay. These are things that you want to clarify, you can copy them down, but if you don't know where they came from, we're out of luck later, right? So yeah, the simplifying part is usually where people get lost, they forget to simplify. But it was v du, and then it simplified just to that. Other questions there? Yes, sir.
So for the first part of the equation, we don't actually do anything with it, right? Like. on the
Right.
side. Okay,
Yeah, that's a really good point. He says for the first part here, we don't really do anything with it. No, all we do with it is choose a u and a dv.
okay, so it's just, the equation is just saying that you pick one and then split it up.
Yeah,
Okay.
and once you pick your u and your dv, you end up these little integrations and derivatives you're doing, and then we just plug them in. But you're right, there isn't actually anything we did to that besides break it up and,
Yeah, because I feel like a lot of people would like in both sides and rearrange everything or something.
right, yeah, the answer will always be whatever's left. Except for one little exception coming up after the break, but we're not there yet. These are good questions. Are there other questions? I can't stress enough about how it pays to be organized. I like to do this off on the side and make sure I have the four, you always need those four things, the u and the du and the v and the dv. Because when we go down to example 1, we're going to need to be doubly organized. Doubly organized. So let's go through that. The formula is still there. I'll put it up at the top of the page here so I don't keep erasing it. We'll do example 1. And that should just about blow our minds enough that we can then take a break, and we'll do some trickier ones after that.
That scared me.
So the formula is, if you have u times dv, it's equal to uv minus the integral of v times du. Hopefully I won't erase it again. No, it's up at the top of the page. So example 1, and you'll see why I skipped over it as my first example. I don't know why I had to listen to this first. So one of the big questions people ask me is, how do I choose u and dv? Besides the fact that you have to be able to integrate your dv, what if you can integrate both of them? I can integrate this, and I can integrate that. So how do you know which one should be u and which one is dv? You can't tell. Yes,
Just
sir.
do whatever one you feel most comfortable.
Technically, you can do whichever one that you feel most comfortable. Yes, that's true. There's a but to that.
Whichever one can be conceivably eliminated later on, like the 2x can eventually, then you take the derivative of that, goes to 2x and then take the derivative of that.
So he's saying you want something that makes things go away later on.
Sine
Something.
of x never goes in there.
If we integrate x squared, what are we going to get? We're going to x cubed. Well, that just made things worse in my mind. We went from squareds to cubes. And then if we integrate it again, for example, it would be x to the fourth. And then if you keep integrating forever, this would just keep getting bigger. But if you take derivatives a couple times, Chad's right, eventually those will go away. The sign, whether you integrate it or take the derivative, it kind of stays the same. It doesn't get worse or better. It just kind of starts repeating itself after a while. So one of the ways to choose is to choose a u that gets better, makes the problem simpler, the exponent smaller. Not always the case. In this case, our dv made things worse, but it did simplify. So if you can't determine which one is which, like in that case, we had no choice because we couldn't integrate the log. If you can't decide, think about which one's going to get nicer when you take derivatives. That's usually going to be your u. But sometimes you try both, and you try one, you're like, oh, that just got worse, and you try the other one. So it's not always obvious which one to do first. So in this case, I am going to let u be x squared, and I'm going to let dv be sine x dx. For that same reason we were just talking about. When I take the derivative of this, it'll get nicer. So that's my original problem. I broke it up into u and dv. So what's the derivative of u? 2x dx. Don't forget your dx. 2x dx. And this is dv, so the integral of v Cosine?
Negative.
Negative cosine? Should we vote? Sure? I don't know if I trust the vote. Sine? Is it cosine or negative cosine? I know which one it is.
Just like,
It's negative? The negatives are getting a little bit more sure. It's negative cosine. Let me tell you guys something. I don't have the integrals memorized. I've got the derivatives memorized. I know the derivative of sine is cosine. And I know the derivative of cosine is negative sine. I got those two memorized, just those two. So if I take the derivative of cosine and I get a negative sign, I'm not gonna get this if I just write cosine. So I would think backwards. If I take the derivative, does it work? And then I get the right sign in there. You don't have to have them all memorized. You can be able to work forwards or backwards. So I got my u's and my v's and my dv's and we're all good. What comes next? What should I do with all those? Yeah, plug it into the formula. Pointing up here.
yeah.
So equals u times v, which in this case is x squared times negative cosine x, minus the integral of v, which is negative cosine x, times du, 2x dx. So I use these four. I plug it all into my formula. I'm going to simplify this so it looks a little bit prettier. Negative x squared cosine x. You guys agree that'll be a plus minus a negative? And I'm putting the x's in the front because I like them better in the front. It doesn't matter. I just like the x's in the front. Minus a negative made that a plus? So last time, after we plugged those in and plugged that in, we simplified, and then we integrated this. Can you integrate that? By looking at it? Hold your head, just explode a little bit. A little bit of explosion. I can't integrate it either. Guess what I have to do? Another one. Integration by parts again. There are some problems where you might have to do integration by parts 2 or 3 times in the same problem. I've got another multiplication, and it's not a U sub problem, so I have to do integration by parts again, just for this guy. This guy's already done. But this is another integral, which is why you want to include your notation. So I'm going to do integration by parts number 2. So this was the first integration by parts, number 1. Now I'm going to do integration by parts number 2 over here. Which one should be u, and which one should be dv? Same thing, he says. Let the u be the 2x, because now we take the derivative, the x's will be gone. And the dv will be the cosine.
Oh, we want to move the 2 in.
It doesn't matter, that's a good point. He says he could bring the 2 out ahead of time, or you could put it in here. The downside of moving it out front is sometimes people forget to distribute it all the way through all this. You do integration by parts. So you can, but then you gotta remember to distribute it all the way through. So I usually leave them in there for that reason, but you can pull it out. You all right with the dx? Excuse me, the u and the dv? Why we have to do it again? The du? Du is 2dx. And v is the integral of this guy. Integral of cosine is positive sign. The derivative is negative. The integral is positive. So that's my integration by parts number 2. That is just for this guy only. So here we go. This whole expression I'm just gonna recopy that front one, because that's still there waiting patiently, negative x squared cosine x, at this part. But then I have plus, and in here is where I'm doing the formula again. So now I have my uv, u, and v. So that's 2x sine x. Minus the integral of v times du, which is 2 dx. Now I'm gonna pull that 2 out, Daniel. Let me pause for a moment. Wait, question? Can you integrate this one? Yeah, finally we get to something we can integrate, that's the goal, get to something you can integrate. The 2 we can just pull out front. So I'm going to recopy these 2. Minus 2 times the integral of sine. Integral of sine is not cosine. Negative cosine. Plus d. So my final answer is negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. What's going on there? You'll start using like a whole page per problem around now. You have to do it twice. Questions on any of those parts? Take some practice. Yes, ma'am.
Wait, so if you integrate it more than 2 times, you have to add the c?
Say that one more time.
Since we integrate it like more than like 2 times, you have to add the c towards the
No,
end.
because there's no boundary.
Well,
But there's no value for A.
The plus c just comes at the very end. I mean, we did integrate in these little portions here, but that was part of the middle of the product rule. So the actual integration came from this very last one here, when we integrated this part. Because everything else was just plugging into the formula. This was when we integrated. And the reason we needed plus c is this was an indefinite integral as opposed to that one that had bounds to plug in.
Oh, yeah, okay. Thank you.
You're welcome. Okay, why don't we take a break? Go get some caffeine, some sugar, some fresh air, do some jumping jacks, whatever it takes. Because it gets a little bit harder. Negative 1. That's my remainder. So the answer is it goes in there once, and then I have minus the 1 over 1 plus x squared. Long division. Something else in the middle of all this other stuff. I am just rewriting that expression that we had. I'm rewriting this guy. So now I have, come on, get this mixed in there. This is the first part, 1/2 x squared inverse tan of x, minus 1/2 the integral of that sum now. 1 minus 1 over 1 plus x squared dx. I rewrote this fraction. Doing some long division. Can we integrate the 1? Good. Can we integrate that? Yes, probably, because we're going to recognize that as, what's that the derivative of? Inverse tan, right? It's going to keep showing up like that all semester long. That's an inverse tan when we integrate it. So finally I have 1/2 x squared inverse tan of x minus 1/2 times, the integral of this guy is just x. The integral of this guy is the inverse tan of x. And I'm going to tack on a plus c. So I'm done integrating. So finally, when I distribute my 1/2 and my negatives, I have 1/2 x squared inverse tan of x minus 1/2 x plus 1/2 inverse tan of x plus c. Thanks. Yes?
So when doing these problems, are the only algebra tricks that we have to consider is this one and moving it to the other side?
So algebra tricks to consider. When you say the only ones, I have to like jog my little memory before I say yes. The one that comes up most often is that one on the left where you move the whole integral to the other side. This algebra trick here, where you, because you have a polynomial divided by a polynomial, that actually shows up not just in this section, but in a couple other ones coming up. So that's in general how you can break down a fraction like that. But I don't think there's too many other ones, other than just typical simplifying techniques where you can, reduce powers and so forth. There will, and maybe if you had some trig, it might reduce as well. Like if you had, I don't know, a sine over cosine, you could make it a tangent or something like that. But the rest of them will be more straightforward. Good question. Imagine what your little brains are capable of. You didn't know that when you walked in today. These are kind of hard. And have I not told you that Math 60 is hard? All right, Math 60 is hard, but it's doable. You just have to be organized and careful and focused and not make any little mistakes. Easier said than done. Okay, before I have you try example 4, I'm going to do the bonus problem. So hopefully you have room on the bottom of that page. I call this the bonus problem. It's the integral of the natural log of x, which most people just Google it when they need to do it. They're like, let me Google the natural log's integral. I can Google it. Google tells me everything. That's good until you're on an exam and Google's not there, or if it is, you're going to get in trouble. So this is actually an integration by parts problem. But what did we say is usually the indication that we have integration by parts? We have multiplication, 2 functions being multiplied. I only see one. The ln x is the only function there. Right? Where's the multiplication?
1 times.
Times 1. So what we're going to do, let's just put a 1 in there. 1 times that. Right? Now I have multiplication. Should the ln x be the u or the dv? It better be the u because we just said we don't know how to integrate it, right? We don't know the integral, so it can't be our dv. It's not integratable, at least off the top of our heads. So we have to let u be the ln x. And dv is just 1 dx. Every once in a while, you'll see a problem where you only have one function, but you can let the other function be 1 and still do this process. Okay, so what's du? 1 over x dx. And what's v? X. Okay, so this should be pretty easy then. Equals u times v, x times ln x, u times v, minus the integral of v times du. Right? V times du, what happens when I multiply those two? It cancels out, I just get 1 dx, right? I didn't write it down. You want me to write it down, or are we good? Those two multiplied give me a 1? We good? Any other question there? Okay, so I have this, and I have this. Now what?
We can just integrate.
Now we can just integrate this. We know how to integrate that. That's my integration by parts, huh? So now this equals x ln x minus the integral of this, which is just x, plus c. That's the integral of the natural log. Some people will write it this way, x times ln x minus 1. Factor doesn't really matter, factor it out. If you Google it, that's what it'll tell you the answer. Every once in a while, LNX shows up in a problem. You can either refer back to these notes, or you can do integration by parts for fun. There's a couple other functions that work that way too. Okay, so here's what I want you guys to do. We have 20 more minutes. Let's see if you can do example, which one was it? Number 4. See if you can do example 4, get the right answer before you leave. I'm holding you hostage to get the right answer.